Well, this looking at the AC current module here, we can calculate these different components. Notice that these the active when we're measuring this thing, this is proportional to the admittance, whereas the impedance would be inversely proportional to the admittance here. So when measuring these type of parameters, usually admittance techniques are preferred over impedance techniques. And I wanted to illustrate another application for organelle modeling using QuickField, and this time we're looking at a mitochondrion. And the mitochondrion is a very inhomogeneous object that consists of two membranes that house the ATP synthase, where ATP is produced inside of the cell, which drives most living processes in the cell and in the human being as well. Now, this is a double membrane it's folded. The interior membrane is folded. These folds are called cristae, and the interior region is called the matrix. And we have these separate spaces here where we're going to have different conductivities and permittivities and so forth. And we want to look at the modulation of the membrane potential due to an external field here. Now, I'm going to model this in QuickField using axial symmetry. So let's look at the model here. Open problem. And this is mitochondrion, which is singular. Mitochondrion. Okay. The geometry is the actual organelle is drawn down here. It's kind of hard to see. We'll have to zoom in a little bit in order to visualize this a little bit better. Okay. Now, these are the block labels. So we have the mitochondrial membrane, the outer membrane. This is the OMM. This is the outer mitochondrial membrane. It's just simply this boundary here. Okay. And it has a permittivity of 12.1 and electrical conductivity from published values 9.5 e to the negative 7. Okay. Now the inner membrane is the one that's folded all into the cristae. And so I've modeled this sort of a convoluted geometry here. Once again, this is rotated about the bottom z-axis of the plane. The intermembrane space is the space that separates the outer and the inner mitochondrial membrane with permittivity of 54 and conductivity of 0.4. The matrix, I've given a permittivity of 54 and a conductivity of a millisiemens per meter. Okay. And these conductivities can vary throughout the, depending on if we're producing ATP and so forth. Now, what we'd like to do is electrically excite the organelle here. And I'm going to go back to my full screen mode. And the edge labels, this is the top edge, and this is it's given a potential of 0.03 volts, and the bottom edge is minus 0.03 volts. And I need to assign a 0 normal condition here. Okay. So I've labeled this edge side, and what I need to do is give it a 0 normal current density. Okay. And this is similar to the models that we've constructed previously. This particular model has roughly 26,000 nodes. The membrane thicknesses have been exaggerated. I'll save changes, and it'll solve the problem here. This one might take a few seconds. Notice I have a finer mesh near the organelle, and I have a more coarse-grained mesh away from the organelle here. If I want an accurate membrane thickness, roughly 10 times smaller, then it's going to require probably an order of magnitude greater in the number of nodes and the corresponding solving time. Okay. So once again, this is AC conduction, and we're solving this at 10 hertz. So we have a 10 hertz driving field, and you can see that most of the field has been screened from the interior of the organelle. Okay. This is rather a rectangular shaped mitochondrion. Most mitochondria don't have this rectangular shape here, and you can modify this and to be even more realistic. Furthermore, the mitochondrion are located inside of a cell, so typically this would be surrounded by a plasma membrane, and we have many mitochondria inside the cell. So we're just looking at one mitochondrion here. And also the plasma membrane has not been modeled. The external, which would be at a much greater distance, the external membrane has not been modeled. So this really more accurately models the case where you'd put microelectrodes inside the cell and excite the interior of the cell by sticking electrodes in the cells. So you can model either situation that you wanted to do by putting an external plasma membrane out here as well. I'll look at the, we can make a contour plot of across the membrane here. If we go to XY plot, and you can see that the electric field once again is in discontinuous jumps. However, the potential is continuous, but not in its derivative across the membranes here. It's very hard to see any variation in the internal membranes. So if we go back, I'm going to clear this contour. Let's do a different contour inside of the inside here, and go across a few of these internal membranes and see if what the field looks like. And you can see, in fact, yes, we do have a much smaller variation. Nevertheless, there is some modulation of these internal membranes in the mitochondrion. Okay, so let's resolve the problem and go to gigahertz regime. I'm going to take this from 10 to 10 to the 10. Okay, and we'll resolve it. Okay, we can view the results. Now we can see right away from the color map, the electric field is greater inside of the mitochondria, and the electric fields are able to penetrate here. And now we're beginning to modulate the internal membrane potentials inside here. Notice these are the sites where ATP is produced. So you might think there were, and there has been some research that shows that external electric fields can in fact modulate the ATP production. Let's look at maybe a contour across some of the internal membranes. Maybe here, XY plot. And you can see that, yes, is indeed a little higher here. Each membrane has a varying potential here because it's a rather convoluted type of shape.